Balance the following equations to indicate whether they are combination, decomposition, or combustion reactions. All right, so in this chapter they introduce the topic of trying to categorize chemical reactions. There's two ways you can categorize chemical reactions. One by how the formula changes, and the other way is by as to why the formula changes. All right, we'll get into the why in chapter 4. So for right now, looking at A, they want you to balance the equation, right? So we call it a combustion reaction. This is how we categorize it, right? So you're burning a hydrocarbon, it's turned into carbon dioxide and water. So if you're going to balance this, balance the carbons first, balance the hydrogens second, and then go back and balance the oxygens. Now with this one, when you count up the oxygens, you end up with 9 on the product side, and you've got a subscript 2 with oxygen molecules. So it's a pain. It'd be nice to get rid of that too. So here's a trick. If you put in 9 halves, all right, 9 halves, all right, so 2 divided into 2 times 9 is 9. And then if you multiply everything by 2 to get rid of that denominator, you'll get a whole number coefficient. 9 halves is a perfectly reasonable coefficient later on in the course, but for right now we're trying to get whole numbers. So multiply across by 2 and get rid of the denominator. Combustion reaction. B, we've got ammonium nitrate decomposing to form dinitrogen oxide and water. So balance it, decomposition reaction. All right, so a simple thing, being pulled apart. Right, one thing being pulled apart into 2. We can categorize this as a decomposition reaction. Another combustion reaction. All right, so balance the carbons first, and then the oxygens, and you've carbons and then hydrogens, then oxygens, and you got your balanced equation again, a combustion reaction. 2 things being put together to form something. This would be categorized as a synthesis reaction. All right, so when we balance the formation of ammonia, we call it a combination or synthesis reaction. Again, the same with potassium oxide reacting with water to form potassium hydroxide. Once we balance it, it's an example of a combination or synthesis reaction. What is the mass in grams of 2.5 times 10 to the minus 3 moles of ammonium phosphate? All right, so we're looking for a conversion factor to get out of moles. An obvious one is molar mass. So if we're given moles of ammonium phosphate, we can add up the atoms in the formula to get the molar mass and use that as a conversion factor to get to grams of ammonium phosphate. And that's what they wanted. So multiply across, the moles cancel, and you're left with grams. B, how many moles of chloride ion are formed when 2.55 moles of are formed in 2.55 grams of aluminum chloride? All right, so we've got grams, and we want to get out of grams, so we can use molar mass to get to moles. So add up the atoms in the formula to get molar mass. And they didn't want moles of aluminum chloride, they want moles of chloride. So if I look at the formula, for every 1 mole of aluminum chloride, you get 3 chlorides, right? 3 moles of chloride, according to the formula. So that's my conversion factor to go from moles of aluminum chloride to chloride. So again, cancel grams, cancel moles of aluminum chloride to get to moles of chloride. What is the mass in grams of 7.7 times 10 to the minus 20 molecules of caffeine? All right, so the way we get out of molecules is to use 6.02 times 10 to the 23 molecules for every mole of caffeine. And now that we're in mole of caffeine, we can use molar mass to get to grams of caffeine. So we have less than a mole, so I expect to have less than 194 grams. Yeah, way less. What is the molar mass of cholesterol when you have 0.00105 moles? What is the molar mass if you have this many moles, and for that many moles you have 0.406 grams? All right, so what's the ratio of grams per mole? So put grams over mole, divide that fractional value of moles into that many grams to get what it would be per 1 mole. So cholesterol, big molecule. Combustion analysis of toluene, a common organic solvent, gives 5.86 milligrams of CO2 and 1.37 milligrams of water. If the compound contains only carbon and hydrogen, what is its empirical formula? Okay, so the way we do combustion analysis is we burn the sample, and when you combust any kind of hydrocarbon, right, the product is water and CO2. So essentially all the assumption here is that all the hydrogen in the compound gets locked up with oxygen and forms water, and all the carbon gets locked up with CO2, So if we can collect the water and the CO2 in some kind of absorber, we can convert from mass of CO2 to mass of carbon, convert from mass of water to mass of hydrogen that was originally in the compound, and then from there get the empirical formula. Okay, so this is what we're starting with, right? We're burning this mystery compound toluene. So in the absorber, I collected this much CO2. So the first thing is, let's get out of milligrams and get it to grams. So I can use the molar mass of CO2 as a conversion factor to go from grams of CO2 to grams of carbon. Out of those 44 grams of CO2, 12 of those grams are carbon grams, right? For every 1 mole of CO2, you got 1 mole of carbon. Now that I'm in grams of carbon, I can use the molar mass of carbon to get to moles of carbon. I do the same thing with the water, except that for every 18 grams of water, 2 of those grams are hydrogen grams. Use the molar mass of hydrogen to get to moles of hydrogen. Now that I have moles of carbon and moles of hydrogen, I take the small value, divide into the other, and try to get a whole number ratio. Well, these are close enough to being the same, right? So for every 1 carbon, you have 1 hydrogen. This is the empirical formula for toluene. Why is it essential to use a balanced equation when determining the quantity of a product formed from a given quantity of reactant? Oh, I think I answered this wrong. I think I was looking at this as just in terms of why do you balance equations, right? Which is to conform to the law of conservation of mass. But really what we get out of balancing equations is a conversion factor, right? To go from grams of one substance in the equation to grams of another, right? So if we look back at a problem before, right, got the balanced equation here. For every 1 mole of this this compound C5H6O, I'm making 5 moles of CO2. That's my conversion factor. For every 1 mole of C5H6O disappearing, I'm making 5 moles of CO2. 65. Aluminum sulfide reacts with water to form aluminum hydroxide and hydrogen sulfide. A, write the balanced equation for the reaction. All right, so what we got to do is get the formulas right for the reactants, get the formulas right for the products. So I have the formula for aluminum sulfide, water, aluminum hydroxide, and hydrogen sulfide. I then go back with coefficients to make sure that the same number of atoms are going into the reaction as coming out. Balanced equation. B, how many grams of aluminum sulfide are obtained? 14.2 grams, from 14.2 grams of aluminum sulfide. All right, so this is a very straightforward mass-to-mass problem. You're given grams of the reactant, aluminum sulfide. Use the molar mass of aluminum sulfide to get to moles. Then use the coefficients in the balanced equation to convert from moles of aluminum sulfide to moles of the product you're interested in, the aluminum hydroxide. And then they wanted grams. Use the molar mass of aluminum hydroxide to get back to grams. Everything cancels except for what you want. How many grams of aluminum hydroxide are produced. 75, aluminum hydroxide reacts with carbon dioxide as follows. All right, so we're making sodium carbonate and water. Which is the limiting reactant when 1.85 moles of aluminum hydroxide and 1 moles of CO2 are allowed to react? All right, so in this situation, the reaction is going to stop when I run out of either of these reactants. So I have to figure out, ask myself the question, it doesn't matter which one, in this case, if I had this many moles of aluminum hydroxide, how many moles of the other reactant do I need to use it up? So I use the coefficients to convert from moles of sodium hydroxide to moles of the CO2. This is how many I need to burn up that 1.85 moles of sodium hydroxide. And then I compare it to what I was given. I was given 1 mole. I only need 0.925 moles. So I have enough CO2 to burn up that amount of sodium hydroxide. So that makes it the limiting reactant. All right, now that we know what the limiting reactant is, how many moles of sodium carbonate are produced? How many moles of excess remain unreacted at the end of the reaction? All right, so go from moles of the limiting reactant to moles of the product you're interested in by using the coefficients. And in order to figure out how many moles of the reactant are left over, the other reactant are left over, take moles of what you were given, subtract it from how many moles you used. All right, I needed 0.925 moles of CO2 to burn up that 1.85 moles of sodium hydroxide. So I didn't use it all, right? I have a little bit left over. So this is what's in excess. And that's how we do limiting reactant problems.